what happens with the fundamental calculus theorem is that finally it's going to bridge the notion between area and antiderivative. Normally we have the concept of an area function is very important for the connection on derivatives and integrals. We're going to start with a continuous function f of t for a number t that is bigger than a, where a is going to be a fixed number. So we can define an area function that is going to be given by the integral from a to x of f of t. Essentially, we'll be analyzing the area below the curve between the point A and the point X as depicted by the limits of integration. Now, we can calculate the net area of this region by multiple means. The approximation will give us the integral at the end, and it will give us the exact value of the net area. When we consider the function of area versus the net area graph, we need to take into account obviously the sign of the area. So just to remind you of that, if you consider, let's say, the area between 2 points A and B, and everything is above the x-axis, then those values are for area are going to be positive. At some point, as we can see here, the function might go into crossing the x-axis and crossing the 0, and then after that we can go into negative values for the function, which in turn for the integral is going to add up negative values of area. And the total area here will be given by this area here minus this area here. Now, how will that look in terms of the function if we graph the function area? So what's going to happen is that initially, if we consider the point A and we take the area at that point, of course the area at that point is 0, and then we're going to start growing our area until we reach C, and then after that we're going to start negative values of area, so the area is going to decrease up to a certain point. Now, to define this properly, consider a function that is going to be continuous, and take the values for t bigger than a. Then the area function for f with left endpoint a is going to be given by the function a of x equals the integral of a to x of f of t dt. This area function gives the net area of the region bounded by the graph of f and the t-axis on the interval a to x. Now, I'll see some examples of this. We've been working a little bit on the notion of positive and negative areas, but now we can translate this directly to the function. So we're going to have two functions here. The first one is going to be the function from -1 to x of f of t, and that's going to be the function a, and the function big F of x, which is going to be the area from 3 to x of f of t. Notice that we can make interpretations depending on the function that we're going to use. So let me just use the board in this case. Okay, let me have a piece of the board here. All right, so we want to find what is a of 3, f of 3, a of 5. Let me change the color here. Okay, gotcha. All right, so a of 3. And just remember that if we're using the area function, it's always good to remember what integral is signifying. So here we have the integral from -1 to 3 of f of t dt. When we go to f of 3 though, we're going to be talking about the integral from 3 to 3. So very quickly we can know that this is 0. In the case of a of 3, we can check that from -1 to 3, we have all this negative area going on in here, and we're going to have that because the area is 27, the integral will be -27. Now, that's for the part A. Part B, let's analyze the same, but for 5. So a of 5, f of 5. Similarly, a of 5 is going to be minus 1 to 3 of f of t dt. And f of 5, from 3 to 5 of f of t dt. Okay, so let's take a look at the function. So if we're going from minus 1 up to 5, we notice that we have a big negative area, which is going to be minus 27, plus then we're going to have this positive area that has measure 3. So the integral a of 5 is going to be minus 24. On the case of big F, though, we have the integral from 3 to 5. And so now we're just only going from this piece to this piece, and the area is only going to be positive, and this is just 3. That means that the integral from 3 to 5 f of t is 3, giving me the value for big F of 3 as well. Finally, let's compare the values for 9. So we can check a of 9 and f of 9. So a of 9 is going to be the integral from minus 1 to 9 of f of t dt, and f of 9 is going to be from 3 to 9. That again according to the definition given by the functions. So for a of 9, notice that we're going from minus 1 to 9, so we're covering all the area. So here we have minus 27 plus the positive area 3, and then again we're going to have a negative area from 5 to 9, which is going to be minus 35. And in total, this is minus 24, minus 35, so minus 59. In the case of f of 9, we're just having the integral from 3 up to 9. So from this point onwards, and we can see this as 3 minus 35 or minus 32. So again, just an example of managing areas between different points, and that's going to be given by where's the particular starting point that we're using, even if it's the same function that we're trying to use for the area. Now, what's going to happen in general is that we can find the relationship between the area below the curve and the antiderivative. And this is going to be one of the scenarios where we can see that. So consider the function a of x to be the area between the area below the curve of f from 2 to x, or also given by the function 2t plus 3. And so if we express the area integral, that's going to give me the function a of x equals integral from 2 to x of 2t plus 3 dt. If we know what this is, it should be easy. One of the advantages is that we can get information about what geometric figure this is. In the past, we've done this using a triangle and a rectangle, but we can do this directly with a trapezoid. Remember that the area of a trapezoid depends on the area of the base and the two different heights that we have for the trapezoid. So in this case, the area is given by 1/2 the base plus the sum of the two heights. And so if we get that, let's get back to the board here. Let's remember we want to get a of x which is from 2 to x of 2t plus 3 dt. But comparing and using the formula of the trapezoid, notice that this area should be equals to 1/2 the base, and the base is x minus 2, which is the difference between 2 and x, times the sum of the two the sum of the two heights. One of the heights is going to be clearly given by the function for the height of the function. So in x, we're going to get 2x plus 3, and that's going to be the height in this point. And when we plug in 2 times 2 plus 3 is going to be 7. So the second height is 7. Now, simplifying this is 1/2 x minus 2 times 2x plus 10. Notice I can factor 1, 2 out of this equation and cancel with the 1/2, and this is going to be x minus 2 times x plus 5, or x squared minus 2x plus 5x minus 10. And this is going to be x squared plus 3x minus 10. So we need to find two particular values, a of 2 and a of 5. So given that, we can know that a of 2 is going to be 0 because it's the integral from 2 to 2. So we know that that is 0, and that makes sense and is going to pan out with this. Notice that this is 2 squared minus or plus 3 times 2 minus 10, and so this is 4 plus 6 minus 10 equals 0. So we confirm that we get the 0. On the other hand, a of 5 is the integral from 2 to 5 up to t plus 3 dt. And that's going to be equivalent here to, we can plug in 5 in here. It's going to be 5 squared plus 3 times 5 minus 10. So 25 minus 15 minus 10. Notice that in this case, we're also going to get a 0. Okay? But this 0 is given more because we have positive and negative area, and this because we're going over the same point. Now, notice that we obtaining a function for the area. So we're having that now my area function can be expressed actually as a function. And so this implies that there's a direct relationship between the function f and certain antiderivative. We're going to have an antiderivative going on in here, and then we can use that. Now, the fact that we plug in 2 and 5 and we can get values means that there's likely going to be a way to use this function to obtain those values, or that we can use define points and get those particular values. And so in general, just to move on and get to the point that I'm trying to make, if you have that a function is continuous and it can be defined in an interval a, b, then the function of the area given by a of x equals the integral from a to x of f of t dt is the net area function. Now, if we make an approximation of that, notice I can do a of x plus h minus a of x. This is going to end up being the height by the function f of x. So we can clearly approximate the derivative, or we can see the derivative of the function a as the function f of x. With that, we can conclude, or we can go directly to the conclusion of this, and is if we have a function f that is continuous in a, b, the area function can be defined as a of x equals the integral from a to x of f of t dt. This is going to be continuous in AB and differentiable in AB, and it's going to satisfy that the derivative of the function is of the area function is going to be the original function. So like we were thinking, there is a relationship between the area and the derivative of the area function, and is that we're going to get a antiderivative relationship with the function inside of the integral. So the area functions end up being an antiderivative of the function f. So now that's going to be really good because of this second part. So now with this, if we have that the function is continuous and we have an antiderivative of function f, then we can talk about the integral from a to b of f of x dx and look at it in terms of the antiderivative. It's just going to be the antiderivative in b minus the antiderivative in a. Okay? And with this, we simplified the notion of doing area under the curve. We don't have to do Riemann sum anymore, and we can just use the antiderivative to compute integrals. Okay, so let's take a look in more details to the anatomy of this. So we have an integral from certain limits of integration a and b. The function f of x is an integrand, and x is the variable of integration. Now for this function f, we're going to have certain antiderivative, and what we're going to do is we're going to do the difference of the values of the antiderivative in the extremes of the function. So we have f of b minus f of a. The shorthand notation for this is going to be f of x between a and b. And so now let's take a look with some examples of how that's going to go into play here. So I'm going to do the first example now and left the second batch of examples for part 2. So let me go with the first example. Now, if we have the integral of 60x minus 6x squared, notice that we know the antiderivative of this. We know that the antiderivative is 60x squared divided by 2 minus 6x cubed divided by 3 plus c. Okay? That is if we have just the antiderivative. I'm going to call this big F of x. Now, if we're talking about the integral between 0 and 10, notice here is where the fundamental calculus theorem comes into play. Because now we can say, oh, okay, so now I just need to do f of 10 minus f of 0. Okay? And so that simplifies so much calculations of area under the curve, because now this area from 0 to 10 is just plug in 10 and subtract the value on 0. Okay, so here we see that we're plugging on the respective values. This is going to disappear, and this c with the minus c is going to go away. So at the end, this is only going to be 30 10 squared minus 2 10 cubed. And this is going to be the end of that example.